Now we're down to our last, certainly not the least, in our speakers. Emmanuel Codillo is a PhD student in Woods Hole in MIT. And we want to hear more about what Eman is up to lately. Eman?
Hi, sir.
Hi, go ahead. The floor is yours.
Hi, guys. Can you see my screen now? Okay. Again, thanks so much for staying. And again, good morning. I'm Emmanuel Codillo, and I'm a graduate student in the MIT who we joined program. And today, I'm going to be talking about the geochemical consequences of rising melange rocks in subduction zones. And I want to start by showing you this map, which shows the distribution of arc volcanoes and subduction zones worldwide. And it comprises approximately 40,000 kilometers of ocean trenches, which are the physical manifestation of the subduction process. Now, it is very important to study subduction zones because this is where we generate the most explosive volcanic eruptions and trigger the strongest earthquakes. And the release of volatiles and gases during eruption can influence the climate and the overall Earth's habitability. So there's plenty of reasons why we have to study subduction zones. But for me, subduction zones are very important because they are the major sites of material and volatile recycling on Earth. And here, subducted materials such as sediments, altered oceanic crust, hydrated upper mantle, and even seawater are brought down to deeper depths to impart the unique geochemical characteristics to arc magmas. That is why arc magmas are geochemically unique compared to mid-oceanic ridge basalt, with enrichment in large ionitophile elements such as potassium, barium, and strontium, and depletion in high field strength elements such as titanium, niobium, and zirconium. However, the actual mechanism of material transfer from the slab towards the source of arc magma is actually still very poorly understood. And there have been a lot of models proposed, but essentially all these models boil down to this classical one, which argues that during subduction, at some pressure and temperature condition, altered oceanic crust dehydrates, releasing hydrous fluids, and sediment melts. And all these melts and fluids rise, percolate, and metasomatize the overlying mantle, which when melted would form your arc magmas. So this model basically argues that the main mechanism of mass transfer is by large-scale fluid or melt percolation. And this classical view has in fact greatly influenced how geophysical observations are interpreted. For example, this is a model interpretation of combined seismic and magnetotelluric data from the Cascades subduction zone, where this highly conductive bright zone were interpreted as a large-scale upward fluid flow from the slab top towards the surface. However, the ambiguity in geophysical observations also led other people to think that this highly conductive region can also be interpreted as hydrated melange rocks along the slab-mantle interface. And new models have been presented highlighting the critical role of melange rocks in subduction zone processes. But what really are melange rocks and how do they form? You can imagine that during subduction, you would expect to have intense mechanical mixing and deformation occurring along the slab-mantle interface, which mixes rocks of different composition. So if we zoom in, you can imagine having blocks of eclogites, metagabbros, metasediments that are surrounded or enclosed by serpentinites. And with time, or as these melange rocks matures, diffusion and fluid advection processes would then convert these distinct blocks into more homogeneous melange matrices, as shown in this pale green matrix. Now, interestingly, the bulk composition of these melange matrix rocks are broadly representative of the melange package as a whole because they form at the expense of and reflect chemical contributions from their protolith. And for that specific reason, why we made use of this melange matrix rocks as starting materials in our experimental study. Furthermore, due to their intrinsic buoyancies, remember that we are expecting to have really hydrated rocks along the slab-mantle interface. Melange diapirs have been predicted to form at the slab top and dynamically mix with the overlying mantle. Now, the critical question for me now is that if melange diapirs can actually form and mechanically mix with the overlying mantle wedge, what would be the compositions of the magma or the melts that you would form from melting of a mantle contaminated with small amounts of these melange components? Essentially, would those melts still resemble arc magmas or not? So such information is critical to determine if melange rocks do play a key role in arc magma genesis. And so in order to test this, we designed a series of high pressure and high temperature experiments using piston cylinder device to investigate the melting of peritite hybridized by small volume proportions of melange rocks. So basically for my PhD, what I do is basically I melt or cook rocks at very high temperature and pressure conditions to recreate the conditions and processes that we think would occur in the deep earth. And for our experiments, we first prepared 3 different starting mixes by combining 85 to 95 volume % of peritite mixed with 5 to 15 volume % of melange matrix rocks. So the figure on the right shows you that the variability in the global melange composition, highlighted in gray circles, reflect first order mixing between 2 end members. One end member is serpentinite here in crosses, and the other end member being sediments or upper crustal rocks. So in order to account for such wide compositional variability, we selected a serpentinite-like component which now comprise the peridotite serpentinite experiments or per-serp experiments, and a sediment-like melange component which now comprise the per-sed experiments. And all these starting mixes were partially melted using piston cylinder device from 1150 to 1350 degrees Celsius at 1.5 GPa. Now let's look at the results. So here's an example of a major element plot of potassium versus alumina, and different compilations of primitive arc melts were plotted here to provide a realistic range of global arc data. So here you have global arc lavas representing mostly arc tholeiites and alkaline magmas, and I also added a subset of alkaline arc magmas in blue circles. And now for simplicity, all these arc data sets now are in the gray and pink fields. And here I also added published experimental melts from hydrous melting of peridotite in blue circle, as well as melts from a mantle hybridized by either slab melt or sediment melt in diamonds. And I also added melts from melting of pure melange rocks in dark blue and red circles. And you can see that in terms of potassium versus potassium and alumina, the hydrous melts of peridotite plotted well within the field of your global arc data, while the melts from a mantle hybridized by either slab melt or sediment melt had very high potassium and did not plot in any of the arc data sets. While melts from pure melange melting also had high potassium, but they plotted well within the field of alkaline arc lavas. Now, ultrapotassic melts such as saucianites also occur in nature, but in much lesser abundance. Now, adding our experimental results here, we show that the melts from a melange hybridized mantle also plotted well within the field of global arc lavas. And looking at other different major element plots, here we're looking at calcium, sodium, and silica versus alumina. Overall, the partial melts of peridotite hybridized by small volume proportions of melange material are similar to hydrous melts of peridotite and better match the alkali and other major element components. Now, in terms of potassium versus silica, so here I plotted the 2 most abundant arc magma types, the alkaline arc magmas in blue circles and arc tholeiite magmas in green circles. And traditionally, alkaline arc magmas have been thought to be formed by flux melting induced by slab-derived fluids, while arc tholeiitic magmas are thought to form by a decompression style melting similar to morbs. Now, adding our experimental results, we show that we are also able to produce the 2 most abundant arc magma types from alkaline melts by melting of a mantle hybridized by sediment-dominated melange materials to an arc tholeiitic melt from melting of a mantle hybridized by a serpentinite-dominated melange materials. So far we have shown that the melts from a melange hybridized mantle have major element composition similar to primitive arc magmas, ranging from arc tholeiites to calc-alkaline signatures. But how about the trace elements? So shown here are NMORG normalized spirogram with different trace elements plotted on the x-axis. And I also added the experimental melts from peridotite sediment experiments and peridotite serpentinite experiments, along with the global arc data in the gray field. And you can see that relative to NMORB, our experimental melts display enrichment in large ion lithophile elements such as barium and strontium, and depletion in high field strength elements such as niobium and zirconium. Now, remember that these are the characteristic trace element signature that define the global arc magmas. And more importantly, we are also, again, we're able to reproduce the two most abundant arc magma types in terms of trace elements from calc-alkaline melts by melting of a mantle hybridized by a sediment-dominated melange to a tholeiitic melt by melting of a mantle hybridized by a serpentinite-dominated melange materials. And again, this is consistent with major elements. So here it seems that the major and trace elements are actually hinting at the same thing. And lastly, arc magmas also show characteristic fractionated trace element ratios. So here I included different trace element ratios such as barium over thorium, barium over niobium, and many more up to thorium over zirconium. And all these trace element ratios have been traditionally used in subduction zone literature. And I also plotted experimental melts from PERSED and PERSERP experiments along with the global arc data in this field. And you can see that our experimental melts also display the fractionated trace element ratios similar to global arc magma, such as we are seeing an elevated in the ratio of barium over thorium, barium over niobium, and many more. Now, it is critical to determine if such fractionated characteristic is just inherited from the bulk starting composition or not. So here we show that so here we show that the bulk starting composition in solid lines plot mostly within the field of the global arcs. And this implies that, the fractionated trace element characteristics can actually be formed early on during the formation of melange rocks along the slab method interface. And these fractionated trace element characteristics are then inherited upon mixing between melange rocks and the overlying mantle wedge. Now, furthermore, we also show that melting of melange hybridized mantle stores can further enhance some of the fractionated trace element characteristics. For example, here we're seeing for barium over thorium, strontium over yttrium, and potassium over titanium, where the bulk starting composition plotted outside the field of global arc data, but upon melting actually enhanced the fractionated trace element ratios of the resulting melt. So in summary, we've investigated the melting phase relation of a mantle hybridized by small volume proportions of melange component using piston cylinder device. And we have shown that our experimental melts reproduce simultaneously the major trace element compositions as well as the fractionated trace element ratios that are characteristic of global arc magmas. And we've shown that depending on the nature or type of melange component and the relative mixing proportion of this hybridizing melange, we're able to produce a wide variety of primary magmas, from tholeiitic arc magma by melting of a mantle hybridized by sediment or serpentinite-dominated melange, to a calc-alkaline arc magma signature by melting of a mantle hybridized by a sediment-dominated melange material. So thus, taken together, we argue that the assimilation of melange rocks into the mantle wedge may actually play an important role in delivering the key subduction signatures from the slab to the source of arc magmas. Thanks.
Thank you, Eman. Quick question, Eman. So I'm trying to remember na my igneous petrology when you were speaking.
Yeah.
Doc Hoy, correct me na lang if I'm wrong, but when a subduction zone initiates, more often than not, I think the signature that we see is of tolytic in character. And then for a more mature subduction zone, then you will see more alkaline signatures. So how does that come to play with when you say that it's actually based on what's the dominant material being melted, whether it's serpentine or sediment based?
So I want to comment first on your first statement that you were expecting, you should see mostly like tholytic character during subduction initiation, and then you later see alkaline magmas in like more mature arcs. So interestingly, the formation of arc tholeiites and alkaline melts are still under like heated debate. And like right now, people are highlighting the critical role of how much water are there in the starting primary magma. But
That's
in
actually
terms
the
of
question of Dr. Yumol to you. How much
oh,
water was in your experiment?
I can answer that. I
So,
will
di ba
first
parang
tackle
less
this.
water for tolytic and more water for alkaline?
Yes, that's true. So the conventional wisdom on the formation of alkaline and tholytic series is by changing the amounts of water, where tholytic differentiation are usually associated with dry primary magmas. So that's basically what we would expect in mid-oceanic ridges and dry subduction zones, while alkaline magmas are usually associated with really hydrous primary melts, where the water effectively suppresses the fractionation of plagioclase. That's how you end up with a alkaline differentiation series. But actually, at the moment, it's still under a very heated debate. And based from my experiments, I'm showing that depending on the nature of the material or the nature of hybridizing component in the source of arc magma, you can produce a wide variety of melts, ranging from arc tholeiites to alkaline. So we're kind of adding like, we are suggesting another pathway of reproducing these signatures.
Thanks, Eman. Bayani?
So what
Yeah,
was Doc Y's question, sir?
it's in the chat, but it's
Oh,
about
okay.
how much water did you place in your experimental batches?
Okay. So I actually did not add any free water in my starting materials. So the bulk water that are contained in my experiments are mainly hosted by the hydrous phases in the mélange hybridizing component. And so the mélange materials that I added had approximately 2.5 weight% of water. So the experiments is actually not water saturated.
Okay. Bayani, you still remember your igneous petrology?
Nako, wala na ako naalala.
Any questions for Eman, Joanne, and Ren?
So I have a few questions, but siguro sa audience muna.
Sige,